Hey, what's going on, guys? Courtney here with a little quick video for you guys. So, in my last post, I was talking about that I came through this breakthrough discovery on something called graph data structures, and particularly, I was trying to figure out a way to start mapping out devices as I start doing audits um, with some of the scripts that I wrote. And one of the things that allows me to do this is graph data structures. So in this particular one, I'm not going to go into the different types of graph data structures. I'm just going to show my implementation, but I'll just go over some of the basic terminology, and then I'll go into show you guys the Python script that I wrote. Demonstrate what a graph data structure looks like, what that looks like from an implementation standpoint, and then also I actually implemented a quick NetMiko script where I actually have on an EVE-NG where I have my Python script going and talking to some live hosts on a lab that I built out, and I ran OSPF between them, and with OSPF I'm able to go into the database, extract the connected nodes, and then build out a map. But essentially, the map is just going to be a text map. I didn't get into the graphical portion of actually using some kind of a visualization library within Python, but I'll show you guys what that all looks like at the end of the day. So ideally, there's portions. There's four main terms essentially what you need to know about maps. Really two: a vertex, an edge, weight, and graph. Now, a vertex, and I'm just gonna show this based off this dude's uh, blog post that he wrote. It's a great blog post. I used it to learn. So if you guys are interested, I'll have the link in the description so you can read it yourself. But ideally, what a vertex is the actual individual nodes of a graph. Then you have the edges, and an edge is essentially the connections between your vertices. So here is a vertex, this is a vertex, and then between that, the lines connecting the vertexes are considered edges, right? And then you can additionally have weights assigned to the edges that shows essentially preference or priority. I used OSPF as the example for the lab implementation because, as we already know, cost is associated with the links whenever the database is calculated, and it used the Dijkstra algorithm to decide what is the best path to utilize for exit and entry out the network. So, not going to get into the depth of what that is, but essentially, the graph is essentially a collection of the vertex and edges that represents this visualized graph. So where this becomes into play, and this is his implementation of it. I didn't copy his because I had a different method of how I did it. So I'm just gonna jump right into the script here. So here, looking at the graph data structure, we'll pull out the graph data structure. So I created a class called graph, and ideally the four functions or four methods that you see here is that I have an add vertex. Now, what that is gonna, well, let me actually open up my constructor class, my constructor method. So the init method here. So within the graph, I have my vertices, and then I also have my edges, which will show my collection of vertexes going into the to the list there. So we have the method of add vertex, add the edge, and then we're gonna get the graph to show what the graph looks like in a text format. And I have a test graph function here to show you guys how it's implemented. So high level, and let me pull up my diagram so you guys can see the diagram that I did for this. So ideally what I did was I created four nodes or four vertexes, and then we're going to call them R1, R2, R3, and R4, right? And this is just without the OSPF and actually looking at the actual devices themselves. But we go into the actual example here. So we have R1, R2, R3, and R4. And then, well, first let me say, let's initialize the graph. We created an instance of the graph class that we created here. Created the four nodes essentially that'll be a part of the part of the actual graph. Now, I added the vertexes, and added the vertexes to the graph. And so what that is doing in the actual function is that it's just appending the vertexes or the vertexes that I'm adding into the list. And then it's also creating an edge on the edges dictionary. It's adding an entry for that vertex name into the dictionary, and then it's making a blank dictionary because essentially I'm not making any connections yet. So these are more of a placeholder. So once I start making the connections, what you'll see here, you'll see that happen in real time. So after I add the after I add the vertex to the vertice list here, and I'll step through it just to show you guys what it looks like line by line. So now that we have the graph and we added the vertexes, we're gonna say vertices, and because I'm not gonna want to print the graph out yet, we can delete that because I'm gonna save that for later. So we're gonna go ahead and run that. So as you can see in the vertices list, it's printing out R1, R2, R3, and R4 as I indicated there. Now it's time to make the connections. So I'm going to make the connections based off of this graph here, right? So we want to make sure that R1 has a connection to R2 with the weight of 15. We want to make sure R1 has a connection to R3 with the weight of 10. R2 has the connection to R3 with the weight of 100, and then R2 will have a connection to R4 with the weight of 25. So what that looks like from a code perspective is that we'll have the graph class, and we're gonna the instance of my graph, and we're gonna add the edge. So ideally we're gonna have the vertice, the V1, vertice 1, and then we're gonna have the vertice 2, so the head point and the tail end of the connection, and then the weight is gonna be assigned to it. Now the implementation might be a little confusing, but I'll try to explain it as best as I can. So ideally what it's doing is it's saying it's going to check if the vertices that I'm providing are already in the vertices list, and if it's true, then on the edges, because we want to also show backwards connectivity, so I don't want to have to. So essentially, if I only do it one time, what'll end up happening is that from the data structure perspective, it's only going to show one side of the connection, and then when you want to look at the connection from the other side, from the tail end of the vertice, it's not going to be there. So essentially in the dictionary, in that edges dictionary, which would have the placeholder here that was created when we added the vertex, it's going to add that vertex name there. It's going to say the tail end of that connection, and then we're going to assign the weight to it. Same as the edges here, we're going to do it on the opposite side and assign that weight as well. So we're going to add the edges there, and we'll go ahead and print that and see what that looks like after we run this line of code. And so there we go. So as you guys can see here, on the vertices is still being printed out there, so you see all the different vertexes that are a part of the graph. And then once we start making our edges or doing our connections, this represents it in a dictionary format. And let me do it in a pretty print because that makes it a little cleaner when we print that out. Yeah, there we go. Perfect. Okay, so as I stated, so in the dictionary for the key, it's going to be the actual name of the router. And then in the dictionary itself, it's going to reference the connection points as well as the weight. So when we go back to the diagram here, and let me see if I can make this a little smaller so we can get that all on the same screen. So on the diagram here, you guys will see on R1, we have the connection to R2 and with the weight of 15, which we show that referenced here. And then R3, we see the connection to R1 and R3 with the weight of 10. Now when we go to R2, we see the connection to R1 to R for R2 going at the weight of 15. So that's the tail end referencing the head end. And then R3 referencing to R2, which is at 100. And then R2 going to R4, which is at 25, right? Now we take it a step further and it repeats itself. Essentially, R3 should have a reference to R1 with the weight of 10, and then R3 should have a reference to R2 with the weight of 100, and then R4, since it only has a single connection in the graph, you're going to see that with R4 connected to R2 with a weight of 25. So this is, like I said, ideally, and the type of data structure that you're looking at here when we're looking at the actual format of this text is what we call an adjacency list. There's a difference between an adjacency list and an adjacency matrix when you want to build this out, but I'm not going to get into the details of that because it gets kind of complicated, and I didn't really draw out a table. I didn't do an Excel spreadsheet to kind of demonstrate what an adjacency matrix looks like, so I'll show you that in another video maybe. But in this particular video, this is only referencing an adjacency list. So each vertex has a dictionary reference to all its individual edges and the weights associated with that edge, right? Now let's take it a step further, and let's say that we want to look at the graph. So we'll go ahead, and in this function here, we have a get graph function, and what this is going to do, and this is where it gets a little I'm going to say super complicated, but I'll walk you guys through what the function is doing when we're actually saying, hey, show me the graph, because I typically don't want to access my edges or my vertices variable. I could have made that a private per the PEP 8 reference, but I typically don't want to access those variables directly. So I created a method that wraps that, and then it actually runs through the graph to make sure that it can build out the vertexes, build out the graph dynamically. So what's going to happen is we're going to have an empty dictionary called graph that's going to be internal to this method here. And then we're going to loop through it. We're going to say for vertex and edges.keys, and that's saying that in that edges dictionary that was generated down here, we're going to extract the keys, right? So that's going to get me the host name here. And then under graph, we're going to make sure that that vertex has a list that's going to be referenced there. And then we're going to do another loop internal to this loop. So per entry, we're going to make sure for edge and self.vertexes, we're going to reference the vertex and get the actual edges for that particular vertex, and get the items, which is the tuples. Essentially, it's going to be tuples that gets generated. And then I'm going to take out of that tuple, I'm going to take the node ID, which is R1, and then I'm going to take the weight, which is 2. And then ideally, I'm going to append it to the vertex list there as a tuple, and that's how it's going to be referenced. So it just makes it a little cleaner, so I don't have to look at it like this. Because once I do it in this data structure here, I'm able to use visualization libraries to easily put this on a nice visual tool like Plotlib or NumPy or whatever the case is. So let's show you guys what that looks like. So I'll run that. And as you can see, now it's a little bit cleaner when you're looking at the graph itself, because the tuples is what's representing the adjacency. So it's the exact same data as the last time. It's just a little bit cleaner because the tuple is a part of a list per vertex, right? So I know that was a lot, but now I'm going to show you guys what this looks like with the OSPF and going into the router, right? So let's go and show you guys my EVE-NG network. So I have 4 routers here, and it's doing the exact same configuration as you saw before. And what's going to happen is I have a script, netmiko script. Well, I used netmiko. Let's go to my main function here. And then essentially I'm going to do the same thing. I'm going to initialize the graph. I have a collection of hosts, and these are all the live IP addresses that I'm using to manage those routers. And then I have a list of facts. And so what I'm going to say is for host and host, I'm going to do the get info function. And what that's going to do is it's going to go through. I created some regex patterns, so that way once I go through and do the show commands on the devices, I can do some matching based on the output of the SSH command. So what's going to happen is it's going to pass the host variable in. It's going to connect to the host. The connection handler gets created here. Once the connection is there, I'm going to say send command, and this extracts the host name, and then I'm going to build the data for the data structure there. It's going to add the host name of that actual device. I did a show IP OSPF neighbors self-originate, and then that regex is actually extracting the connected neighbors, because instead of looking at one router, because essentially I could technically only look at one router and then build out this graph by looking at one router, because OSPF is link state. But for the sake of this example, I went through and I did a show IP OSPF router self-originate on each device and made sure I'm only looking at the database from that router's perspective instead of trying to look at it from every single the entire router LSA database. Instead of looking at all the type 1 LSAs in the database. So, and then I'll go through and extract the router ID from the neighbors, and then essentially it'll print out that data structure, and then it'll do the connection. So, well, and then it'll build the graph for me, which it happens down here. So let me show you guys what this looks like. I built it on my dev box. Let's clear. And so let's do this. So we're going to say run Python main. And so what'll happen here is that, let's make sure this is going to connect. See, this is sometimes that sucks with these connections. I don't know why it's doing that. I hate when that happens, don't you? Make sure cat main.py. So it's all there. You know what we'll do is that just to make sure, we're gonna rm main.py, and I'm just gonna go into the script and then nano main.py, paste that in there, and then we're gonna clear, and then we're gonna say python 3 main.py. There we go. Oh, no wonder. So let me go back and under the test graph, what we're gonna do is we're gonna run the main function there, and let's remove that again, nano that up, bam, and then we're gonna clear. There we go. So it's now logging into each router within the lab, and you see it post what the data that it extracted out. And like I said, it's because it's doing an SSH command. I didn't do this in a this is running in a parallel configuration. I didn't really, or a linear execution. So it's going line by line. And then after it talks to all the routers, it's going to build the graph data, and then it's going to show me the results based off of the graph. So as you see, it's all ones for the weight because I didn't actually go through and grab the OSPF cost off those interfaces. I'll probably implement that later, but ideally I just wanted to reference that the connections are there. So if we go back to the topology again, and we just make sure that what we see there is what is being represented. Let's go there. Oh no, don't want to do that. So here. So back again, we go to R1, and then we look at its connections. So R1 has connection to R2. R1 has a connection to R3. R2 has a connection to R1. R2 has a connection to R3, and then R2 has a connection to R4. Then R3 has a connection to R1. R3 has a connection to R2, and then R3 does not. And then R4 has a connection to R1. And because, like I said, I'm only focusing on the OSPF database, these management links that I'm using to get into the routers is not being checked. That's because it's not participating in OSPF itself. So as I add more links, I can actually actively go in and build a live topology map without actually having to go into each router and understand what the topology looks like. Now, what this opens the door for me is that it allows me to do a lot of cool things. Now, one of the things that I have an idea for is SD-WAN stuff. You know, building out networks and doing optimization, but then I can use these graph data structures to actually make decisions for devices and actually have it send the commands to the devices to, you know, either optimize traffic or do traffic engineering for me without actually having the routers do anything. So it's like making my own external controller. That the possibilities are endless with this, but I just wanted to show you guys what that looks like from a configuration, from an implementation standpoint using Python. But yeah, if you have any questions, let me know. pretty excited about this. Let's just say that I'm gonna have a lot of fun in the future. All right. Well, thank you guys for listening, and let me know if you have anything else you'd like to check out. Later.